Hey guys, today we're going to talk about support vector machine. In this video, we will discuss the basics of support vector machine and understand how support vector machine works step by step. So what is support vector machine? SVM is a supervised learning method that looks at data and sorts it into one of two categories. An SVM output maps the sorted data with the margin between the two as far apart as possible. Let's talk about the objectives of support vector machine. The main objective of support vector machine is to find a hyperplane in an n-dimensional space that distinctly classifies the data points. The dimension of hyperplane depends upon the number of features. If the number of input features are 2, then the hyperplane is just a line. And if the number of features are 3, then the hyperplane becomes a 2D plane. Now let's talk about the real-life applications of SVM. Consider a simple road with two lanes. The two white lines are drawn as border of an road, just like support vectors in SVM. And the yellow line is a separator that needs to be in a way that widens both the lanes equally. Or should I say, it should be in a way that maximizes margin of the road. Now let's look at how SVM works. Consider a one-dimensional data set about students' marks. The red point indicates failed students and the green point indicates the passed students. What happens when we set a threshold over here? If we put our threshold over here, then the distance between failed students and the threshold would get smaller. That is, the probability of getting a pass student becomes higher. On the contrary, if we shift our threshold and move it over here, then the distance between pass student and the threshold would become smaller. That is, the probability of getting failed students become higher. So the best approach here would be to place our threshold midway, so that it is equidistant from both groups, where D1 is equal to D2. Here D1 and D2 are the distances between the threshold and its closest observation, also known as margins. Thus we can say that SVM is maximum margin classifier, as it gives largest margins to make classifications and hence reduce the chances of misclassification. Now let's suppose we get an outlier over here. Although the student's marks are above the threshold, he has been wrongly said to have failed due to some technical error. Then in this case, due to the outlier point, our threshold shifts and moves closer towards the passing points. So now if a new point enters near the passing students, it would be incorrectly classified as failed because it will fall behind the new threshold. This happens because support vector machines are sensitive to outliers and our SVM model has fit the training data way too perfectly. So what do we do now? We must simply allow some error to occur on our training data so that we get a more generalized model. So again, by placing the threshold midway, here these 2 points are the support vectors. So when we allow misclassification, the distance between the threshold and the support vector is called soft margin. Cross-validation decides the best threshold that would give minimum misclassifications. For instance, if cross-validation decides that this was the best soft margin, then we would allow only one misclassification and 2 correct classifications. Let's see how support vector machine in 2D looks like. Now it is time to turn the one-dimensional dataset into 2 dimensions by adding a feature called study hours. We simply plot all the points onto the graph. Now how do we know which line is the best separator? Whether it's this line, or this line. For that, we will take this line, draw the margins with the help of support vectors. Then we take this line and draw the margins with the help of support vectors. And then we take this line and draw the margins with the help of support vectors. This line gives the maximum margins and will become a hyperplane. line that gives us maximum margin is called a hyperplane. Measure the distance of this point from the margin. Measure the distance of this point from the margin. These 2 points, the support vectors. Notice that our threshold in one dimension will become a line in two dimensions. As seen previously, we would use cross-validation to allow misclassification of an outlier point to get a more generalized model. Here is an SVM model with high regularization, and here is an SVM model with low regularization. While implementation, we can set regularization parameter C to low in order to allow misclassifications and get a more generalized model. Let's see how support vector machine in 3D looks like. SVM in one dimension contains student's mark. SVM in two dimension contains student marks as well as study hours, and SVM in three dimension will consist student marks, study hours as well as age of the student. Here is SVM in three dimension where the line becomes a hyperplane. And on the left side of the hyperplane we have failed students with lesser study hours. And on the right hand side of the hyperplane we have past students with more study hours. Here the points that seem closer and bigger represents younger students, and the points that are smaller and farther represents older students. Until now we have only talked about linear support vector machine. What about non-linear support vector machine? In non-linear data, the points cannot be separated by a hyperplane. In non-linear data, we have a lot of overlapping happening. So we transform the non-linear features for higher dimension. We use a kernel function to transform non-linear data. These are the two most popular kernel functions. First one is radial basis function, that is RBF. Here the RBF function for 2 points x1 and x2 computes the similarity of how close they are to each other in infinity dimensions. The second kernel function is polynomial kernel function. Polynomial kernel simply allow us to calculate the dot product of 2 points by increasing the power of the kernel. After the transformation, we then separate the data using a hyperplane and finally project the points back to the original space. Note that in kernel functions, we calculate the relationship between each pair of points in a higher dimension, but we don't actually do the transformation. So this technique of calculating high dimension relationship without actually transforming the data into higher dimension is called the kernel trick. The kernel trick reduces the amount of computation required for support vector machine by avoiding the high-level maths involved in transforming the data from low to high dimensions, and thus making calculating relationships in infinite dimensions possible